So we will start from with a talk on differential privacy by Markus de Medeiros. He's now at AWS. And all the talks are 20 minutes. There was no strong guidelines on the length of the talk versus the question, so we will be around 16, 17 minutes for the talk and then the rest for questions. Thank you. The floor is yours.
All right. Thank you, Thomas, for that introduction. I'm Markus. I'm a PhD student at NYU and a research intern at AWS. Today I'm going to be telling you about SampCert, our project for doing verified differential privacy in Lean. Okay, imagine you're a statistician. You can picture that your day job amounts to collecting data from public and private sources, organizing and computing over that data, and finally, generating some statistics and decisions based on your data, which you send out to the public. So given that your data may be private, you want to ensure that your statistics don't accidentally release any information that you don't mean to. For example, you might work at the US Census Bureau. It could be okay to release the maximum income reported by a zip code, but not the income reported by each address. Okay, now in a perfect world, every statistic you release would only disclose the aggregate information about your data set that you meant to. However, and I hope this isn't a shock in the security session, but the world is far from perfect. Attackers have found very clever ways to learn a great deal of sensitive information using only unintentional data leaks in innocuous-looking statistics. So going back to my example, knowing the maximum income reported in a zip code also tells an attacker that somebody with that precise income does live in that zip code. This, on its own, can be enough to identify them. By leveraging automated constraint solvers and correlations with public knowledge, attackers have managed to target and re-identify individuals even in real-life data sets which use traditional anonymization techniques. Okay, so what can be done about this? Well, privacy researchers have defined this notion called differential privacy, which establishes a bound on the amount of information that an attacker can learn about your data set given any statistic. While these re-identification attacks are remarkably effective, it turns out that they're also very brittle. And so by adding the right amount and the right kind of random noise to your statistic, you can ensure that even very strong attackers will learn very little about your true data. Okay, so that's great, right? Problem solved? No, sadly. There's still, 16 minutes left here. Well, everything I've said so far is true on paper. That, of course, doesn't necessarily mean that it's true of your code. So on the slide, I have the Laplace distribution. It's a continuous probability distribution that you might want to draw samples from in the process of making your statistic private. And you can implement a Laplace sampler using traditional floating point techniques. On this scale, your distribution will look fine. However, in the early 2010s, a researcher named Ilya Mironov discovered that when you zoom down to the bit level, you see that some values are sampled with the incorrect probability and other values never get sampled at all. Mironov used the gaps in this distribution to mount a re-identification attack, which affected several of the commercially available differential privacy libraries at the time. Now, since then, many of them have patched this exploit, and many other exploits have been found. But the point I really want to impress upon you here is that in differential privacy, even tiny deviations from the algorithm that you've analyzed on paper can severely affect the security of your entire system. At AWS, we offer a service called Clean Rooms. Clean Rooms lets our customers compute over and privately share statistics about their data. So naturally, we want to deliver them the highest degree of security that we can. To that end, we decided to verify some of the components of clean rooms related to differential privacy. So here's our problem. We want foundational verification. We don't want to, for example, assume that floating points are an accurate representation of the reals. We want to make use of the large body of existing theory in differential privacy. Our job is to not come up with new differentially private algorithms, but have high assurance implementations, the things privacy researchers have already figured out. And finally, we want an implementation which our privacy team will be able to integrate into our existing services. And of course, because this is AWS, this means our implementation has to be efficient at scale as well. Our answer to this challenge is SampCert. SampCert is a differential privacy library written and verified in Lean. It uses the large body of verified mathematics provided to us by MathLib in order to mechanize even recent privacy research. And finally, the compiled code that we get out of SampCert is competitive enough in terms of performance to be used and is currently deployed at AWS. Okay, so for the rest of this talk, I'm going to walk through the components of SampCert from the ground up, and I'll highlight what we think makes SampCert an effective way to get these concrete privacy guarantees in practice. So to start off, the real beating heart of all differential privacy is the ability to generate specific kinds of random noise. So we're going to begin by formalizing the semantics of a probabilistic programming language. A probabilistic program is one which, when executed, draws a sample from some probability distribution. There are many ways to represent these languages, but for us, we're going to use what's known as a shallow embedding into mass functions. This means that in Lean, we represent all of our probabilistic programs as Lean functions from a type to the real numbers. And this represents the probability of sampling any given point. To construct these mass functions, we're going to define a small DSL, which consists of 4 basic constructs. The return operator sample is a mass function which samples a single value with probability 1. The uniform byte operator samples uniformly from the first 2 to the 8 natural numbers. The bind function is a monadic bind, which allows us to sequence 2 random computations. Finally, we have a while construct, which is defined mathematically as a limit and allows us to simulate the effect of executing an unbounded probabilistic loop. Okay, so despite the simplicity of this language, we found that it was enough to encode the kind of sampling algorithms that we found in the literature. For our application, the programs we want to verify are all small, stateless, first-order programs, which nevertheless have security proofs which are quite mathematically involved. Okay, so what I want to stress here is that when we write code using our DSL, what we're really doing is describing a particular mass function to Lean. This means that in SampCert, we can encode programs, specifications, and proofs all in the language of plain Lean terms, and then we can make use of Lean's well-established techniques for mechanizing mathematics to get the program correctness proofs we're after. I'll give you an example. So in differential privacy, you often want to sample from this distribution. It's called the discrete Gaussian. The discrete Gaussian was developed in the early 2020s as an alternative to the continuous distributions I was talking about earlier. So the formula I have on the slides is a little scary. It involves, I don't know, transcendental numbers, big sums, division between reals. But there's also a very clever algorithm developed by Kanon, Kamath, and Steike for sampling exactly from this distribution. Okay, so what we do in SampCert is we translate this function, or this program, into a mass function by writing it in our DSL. We can turn the specification into a mass function by writing down that formula. And then finally, our verification challenge is to prove that the mass functions for our program and for our specification are mathematically equal. Again, this is a hard problem in general, but we can lean on the fact that we've embedded ourselves in a very rich mathematical landscape, and we can use the math afforded to us by MATLib to mechanize the proof from the Kanon, Kamath, and Steike paper as well. Okay, a couple more words about this shallow embeddings point. We found time and time again that the modularity afforded to us by this proof technique was very useful. Once we've proven that a program and its specification are equal, it means that we're able to use them interchangeably throughout the rest of our code base. So for one, this means we get functional modularity for free. We can always rewrite a program into its spec in any Lean code which uses it. It also means that for proving program properties like termination, normalization, and support, we're able to prove them about the specification instead of proving them about the program. So it can be easier to just analyze the PMF of a spec rather than trying to come up with proof rules that work with loops, for example. Okay, finally, this means that we're free to switch between different optimized versions of our program. And we do this in SampCert. Late in the development, we found an alternative way to sample from the Laplace distribution. And so we were able to add on dynamic switching between these different sampling algorithms because in Lean, mathematically, they're all equal. We didn't have to redo any of our security proofs. Okay, so we've built up this language for expressing and reasoning about probabilistic programs. Now we want to start talking about privacy. As I alluded to before, a differentially private program is one which produces a randomized value from a database such that the output is not too sensitive to the contributions of individuals. More concretely, a program is epsilon differentially private when for any 2 databases that differ by 1 row, the resulting probability distributions will be within epsilon of each other. Intuitively, when epsilon is small, an attacker would need a huge number of samples in order to determine which distribution the program is sampling from, and therefore which database contains our true values. Okay, so you might notice that there's some air quotes on the slide here. And so while it is true that privacy researchers, generally speaking, agree of this type of framework, there are a lot of variants for what within epsilon is supposed to mean. So on the slide, I have a selection of them, but don't worry, there are even more. And they all provide slightly different privacy guarantees, slightly different composition theorems, and there's many different conversions found between them. It's quite a situation. Okay, so despite this, we noticed that at a high level, there's a common collection of features that these definitions tend to share, and that a lot of differentially private programs tend to rely on. So in SampCert, we collected these features together into an interface we call abstract differential privacy. The interface has three parts. For one, it parameterizes by a proposition of one real valued parameter, which is meant to define how you measure the privacy of a noisy query over a database. Our interface requires that your definition for differential privacy obey a set of rules, in particular adaptive composition, post-processing, and the constant rule. And then finally, our interface requires that you have to have some way to make a query over integers private. So in particular, we require that for any integer valued query over a database that has an upper bound on how sensitive the function is to changing individual rows in the database, there must exist some noise distribution so that your query plus that noise is epsilon differentially private. In SampCert, we've instantiated this interface with the two variants that we most care about at AWS. That is pure DP with noise drawn from a discrete Laplace operator, and zero concentrated DP with noise drawn from the discrete Gaussian. There are other variants of DP, which we are pretty confident fit into this framework, but we just haven't mechanized them. And the proofs that these DP systems satisfy these bounds are mathematically quite involved. So in particular, the zero concentrated differential privacy proofs involved like Jensen's inequality and Fourier analysis. Using the math that we found in MATLib, we were able to replicate these proofs from the literature, which saved us a lot of thinking. OK, to finish up this section, I'll just quickly show you what this interface can do. On the slide, I've got a small program which builds a histogram out of your data and then makes it private by adding noise to the count in each bin. Now, I won't get into the proof in too much granularity here, but if you kind of go through it step by step and apply the rules from the interface, you end up with an abstract privacy bound, which applies no matter which instance you use. I can speak more to the pros and cons of this afterwards. I'll say that it's nowhere near a complete proof system, but we found that because so many of these definitions share these common features, you're able to generalize some of the proofs that you might see in the literature, and get guarantees that apply for all of these different variants. OK. So finally, we've developed this theory of differential privacy in Lean. We want to actually deploy it out in the world. You'll recall that we've shallowly embedded our programs into this type of mass functions. And so in Lean terminology, this type is non-computable. It's just a function from a type into the real numbers. The Lean compiler doesn't know how to get a binary out of these functions, and it definitely doesn't know how to interpret them as probabilistic programs. But you'll also remember that our programs were not just general or just arbitrary mass functions. We decided to write them using this little DSL. Okay, so this carves out a subset of these mass functions, which are distinguished by the characteristic that they do have a known sampling algorithm. So how do we make use of this? Well, the 4 terms in our DSL were chosen not just because they were straightforward to reason about mathematically, but also because they tightly correspond to the terms in an imperative programming language. So in SampCert, we're able to use the Lean foreign function interface to attach a C++ implementation for each of these terms. And this means that Lean can then compile PMFs that we write in terms of this DSL into genuine randomized programs. I mean, in Lean terminology, we're able to remove the non-computable marker once we do this. Even once you add back in all of the Lean boilerplate you need, this amounts to around 50 lines of trusted C++ code, which mostly amounts to ensuring that you apply the right functions to each other in the right order. And it's well within what we consider acceptable from a security standpoint. OK, so what does this 50 lines get us? Well, at the beginning, I asked you to imagine you're a statistician. So I hope at the end here you'll enjoy a graph. Here we've got the performance of our discrete Gaussian sampler compared against the publicly available implementations that we were able to find. Our extracted code has performance which is competitive with these publicly available libraries. And of course, our implementation is substantially more robust because it's derived from a verified implementation. Not to put too fine a point on it here, but the code that we're running to produce this graph is currently deployed as part of clean rooms. OK, I think that's just about my time. So thank you for your attention, and I'd be super happy to take any questions.
Any questions? Should go to the mic.
Hi, thank you for the very nice presentation. So you started the talk by showing that sort of the discrete Laplace has some floating point error and that loses the guarantees. But your lean system formalizes the samplers over real numbers. When you extract the C++ code, are you careful about the floating point errors? Are you using arbitrary precision, rational arithmetic? Can you clarify that gap?
Yeah, so our samplers that we extract are over the integers. They're not over the real numbers. So we use the discrete distributions, and so we avoid using floating point numbers in that case. The type of our PMFs is t to the real numbers, but we interpret them as a randomized value of type t. So we don't have to interpret the real numbers in order to execute them. We do think that floating point calculations could fit into this framework. I mean, probabilistically, it's fine. They're countable and discrete. But we haven't done any of that work. We'd be interested to in the future. Does that answer your question? Or?
I was maybe wondering that the probabilities are real numbers.
Yes.
Right?
Yeah.
So it's true that it's a discrete Gaussian over the integers, but
yeah.
the individual probabilities are reals. They're irrational.
That's exactly right. That's exactly right. So the sampling algorithms we use, they all use rational arithmetic. Mm-hmm. There's no interpretation of reals in that case.
I see. And then all of the other operations in the DSL, maybe if you add numbers or divide them, etc., you are also not suffering from numerical error?
Exactly. They're all exact.
All exact.
They're all exact.
Very good. Thank you.
Thank you so much. So in this slide, at the last bullet point, it is stating that this is deployed at AWS. Right. How much can you disclose what kind of real-world application there is a demand for the DP? And then in what scale did you address the problem? Thank you.
Yeah, sure. So there's not much I can talk about, mostly because I wasn't the one who did I don't know, I worked in Lean. I didn't do the crazy stuff of actually getting it out there. I know that the sampling algorithms, our implementation of those are definitely deployed. And then I think the idea is over time to get higher assurance for the rest of the differential privacy suite, but I'm not sure that those are in use right now. Yeah.
Hi, thanks for the nice talk. About the C++ extraction, basically. So just from the snippets you showed, that basically looked like you're taking the pure Lean program and embedding it into I/O. Could that have been a meta program in Lean as well?
So yes, and that's what we did at first. But when you use a meta program, you also have to translate all of the rest of the pure Lean code as well, right? Like if I do integer, well, okay. If you wanted to go within Lean, yes, I think that could be a meta program, and that would be sort of interesting. We used a meta program at first to go from Lean to Daphne for other deployment reasons. And then we ran into issues where we had to do meta programming that the Lean compiler was already doing, like compiling Lean edition to Daphne edition,
right.
which was quite a nuisance. But it could be interesting to go Lean to I/O Lean.
Yeah, could even be faster than the apply course.
Yeah, cool.
Thanks.
Good suggestion.
Okay, let's thank our speaker again.